Picking up with question number 21. Which of the following would be classified as categorical data? So we've got to know what categorical data means. If we go to our book, I'm not sure if any of you have used this function. There's a little search bar here. You can click this, and if I was to search for categorical, let's see. Yeah. Let's see, C-A-T-E. Categorical. You see it brings up in chapter 1 here all the places you see categorical data, categorical data. Then you can click on categorical data and it'll show you, places where it's been used. And so this one here, if you click on the second one, that'll go to where it's actually defined. Alright, so quantitative data or numerical data consist of numbers representing counts or measurements. Categorical data consist of names or labels that are not numbers representing counts or measurements. So let's go back to the test review. Which of the following would be classified as categorical data? Amount of rainfall, I believe that's like a number, right? Number of suitcases on a plane, of course that's a number. Tree height, that would be a number. Hair color, not a number. Red, black, brown, blonde. So hair color would be the correct answer. Alright, going back to levels of measurement. Which level of measurement consists of categories only, where data cannot be arranged in an ordering scheme? That is the simplest order, the nominal level. Which level of measurement consists of categories? I think I just did that. Alright, next question. What is the difference between a random sample and a simple random sample? Alright, so let's see where that is in the textbook. So random sample. Definition of a random sample. Alright. A simple random sample of n subjects is selected in such a way that every possible sample of the same size n has the same chance of being chosen. A simple random sample is often called a random sample, but strictly speaking, a random sample has a weaker requirement that all members of the population have the same chance of being selected. That distinction is not so important in this text. Alright, so simple random sample, you pick, say you were going to pick groups of 5 people out of a classroom, and you want to make sure that it's picked in such a way that every possible sample of size n has the same chance of being chosen. So if you're picking 5 out of a classroom, you need to maybe put all, say, 30 people's names in a hat and then draw out 5 and then put those back in and then draw out 5, so that everybody would have the same chance of being selected. Alright, let's see what the choices are. Of course we see the right one, but let's see what the choices are. With a random sample, each individual has the same chance of being selected. Well, that's correct. With a simple random sample, all samples of the same size have the same chance of being selected. It's also correct. Let's see what the other choice was. it looks like it's just the opposite. With a random sample, all samples of the same size have the same chance of being selected, so that's wrong. And with a simple random sample, each individual has the same chance of being selected, and that's wrong. Determine whether the description corresponds to an observational study or an experiment. So let's look at observational study real quick. Okay. In an observational study, we observe and measure specific characteristics, but we don't attempt to modify the subjects being studied. So you're just observing. In an experiment, we apply some treatment and then proceed to observe its effects on the subjects. So an experiment, you do something to the subjects, and then you want to see what it's going to do to the subjects. 50 patients on dialysis are divided into two groups. One group receives an experimental drug to fight cancer, the other a placebo. After 2 years, kidney functionality is measured. So they did something to a group. That's going to be an experiment. Now, if they would have just taken a group and did nothing to them and just observed them, then it would be an observational study. Since they actually did something to the group, it's an experiment. In a study of 446 men with a particular disease, the subjects were watched while asleep. So they were just watched. It didn't say they were, given a comfortable pillow or a drug or anything like that. So since they were just watched, that's going to be an observational study. Which of the following corresponds to the case where every sample of size n has the same chance of being chosen? Alright, that would be a simple random sample. That's what we just went over. So, yeah, simple random sample. After constructing a relative frequency distribution, summarizing IQ scores of the college students, what should be the sum of relative frequencies? So let's take a look at a relative frequency distribution real quick. Let's see. Relative frequency distribution. Alright, a variation of a basic frequency distribution is a relative frequency distribution, or a percentage frequency distribution. So the way that this works, you got to see how many, like in each class that you would have, and then instead of just writing down the number, like how many in each class, you take the number, like how many in each class, and divide by the total number of data items, and then multiply by 100. That'll give you a percentage. So for the one that we're looking at here, it says there are 78 data items. So to get this first percentage here, it says there were 2 that were an IQ score of 50 to 69. So you take that 2, divide by 78, and then multiply 100 by 100, and you get 2.6% if you round to one decimal place. So it says the sum of the percentages should be 100%, with a small discrepancy allowed for rounding errors. So a sum such as 99% or 101% is acceptable. Since you are, in this table, you're rounding, you see, to one decimal place. Since you're rounding, sometimes whenever you add all those up, you'll be close to 100. So that is okay. Let's go back to the problem. After constructing a relative frequency, what should be the sum of the relative frequencies? We just said it should be 100%, but it could be just right around 100. And this says if percentages are used, then the sum should be 100%. If proportions are used, that would be fractions, then the sum should be 1, because 1 is the same as 100%. Alright, identify the class width, the class midpoints, and class boundaries for the given frequency distribution. Okay. So let's look real quick at what those actually are. Alright, so we want to find class width. The class width is the difference between two consecutive lower class limits. So these are the classes here: 35 to 37, 38 to 40, 41 to 43, 44 to 46. The smaller number in each class, that's the lower class limit. The larger number in each class, that's the upper class limit. Okay. The number between 37 and 38, you say there's no number there. Well, if you take the difference between the two, you get 1 half of that is 0.5. That's how we're going to get the actual class boundaries. I saw this definition here. Numbers used to separate classes, but without the gaps. Class midpoints, you can take and add the upper and lower class limits and then divide by 2. That gives you the class midpoint. Alright, so class width, the difference between two consecutive lower class limits, or yeah, so that's what it is. So 35 and 38, the difference. 38 minus 35 is 3. Or 41 minus 38 is 3. Or 44 minus 41 is 3. So that's why there's an answer of 3 here. What are the class midpoints? Alright, you take the difference between an upper class limit and a lower class limit. So it would be like 38 minus 37, that's 1 unit, divide by 2. So 1 divided by 2, that's 1 half, or 0.5, right? So what we'd want to do to get the class midpoints is we would want to add 0.5, not class midpoints, I'm sorry. We're doing class midpoints. So I was talking about class boundaries. I apologize. Let's go back to class midpoints. To find the class midpoints, then you just add the lower class limit and an upper class limit, divide by 2. So it's actually a lot easier. So 35 plus 37 divided by 2, that's 36. 48 plus 40 divided by 2, that's 39. 41 plus 43 divided by 2. And I'm wondering, this must not show the entire set of data because I don't see any other classes here. A full set of data. So this should, this should be the only thing that's required is right here. I don't see, oh, okay, I see more here. Alright, so this table is, it's like it's broken into 2 pieces and it's side by side. I didn't see that at first. Alright, so you add the two together, divide by 2. Add the two together, divide by 2. Add the two together, divide by 2. That's how we get all these class midpoints. Now what I was talking about earlier, the class boundaries. You have to take the difference between an lower class limit and a previous upper class limit. So that gives you one unit. So you take 1 and you divide by 2, you get 0.5. Alright, we start off here at the smallest lower class limit. Subtract 0.5 from that and you get 34.5. That's your first class boundary. Then take the upper class limit of 37, add 0.5 to that. That's 37.5. Then take the next upper class limit, 40, and add 0.5 to that. And we keep going on. Now we just add the 0.5 to every upper class limit until we get to 55.5, and that will be your last one. Alright. And number 30, construct one table that includes relative frequencies based on a frequency distribution shown below. Then compare the amounts of tar in non-filtered and filtered cigarettes. Do the filtered cigarettes appear to be effective? Hint: the filters reduce the amount of tar ingested by the smoker. Alright, and so you have to click here to actually get the set of data to look at it. And we're doing a relative frequency, so we have this in a frequency distribution. We want to make it a percentage. So the way we do that, see, tar in filtered cigarettes, tar in non-filtered. So they just have the classes listed for both. You can see that the non-filtered cigarettes, their tar does start 13 to 17, so anything before that is going to be 0% for the non-filtered cigarettes. And if you look right here, non-filtered, 3 to 7, see, there's no 3 to 7 with non-filtered, so it's 0. 8 to 12, 0 again, because that's less than 13. Now, when you get 13 to 17, you can see there's 1. Alright, and so we need to get the total number of all the frequencies for non-filtered. So 1 plus 16 plus 7 plus 1. So that's going to be 25, I believe. 1 and 16 is 17, and 17 and 7 is 24, plus 1 is 25. So what we want to do, we want to take, alright, we have 1, and we want to divide that by 25. That's going to give me a decimal. So 1 divided by the total number of frequencies, 25, and I get 0.04. Say that times 100, and that changes it to a percentage. So what I need is to put 4% right here. So I multiply that by 100, that would be 4%. 18 to 22, 0. So 0 divided by 25 is 0. So that's why there's a 0%. 23 to 27, we have 16. So we need to say 16 divided by 25 and say that times 100 to get a percent. So it's 0.64. So that times 100, that'll be 64%. So you see right here, 64%. 7 is the next one. So 7 divided by 25 is 0.28, so that's 28%. And then the last one is 1. We've already figured out that when you have 1 in a class for this one, that's 4%. So that's why they have 4%. Now, this relative frequency distribution here is used for filtered cigarettes. So that's where the second column comes in. 3 to 7 is 2. So total number, again, let's see, that's 20 and 5. So that's 25. So you say 2 divided by 25, and you're going to get 0.08. So that times 100, that's 8%. And then 3 divided by, so let's see, then we need to do 3 divided by 25, 12.12, so that's 12%. So on and so forth until, notice your largest one is 22. So anything past this class for filtered is 0, 0, 0%, because there's nothing there past 22 for filtered. Alright. Do the filters appear to be effective? Well, filtered has all the lower tars, where non-filtered has all the higher tars. So yes. Let's see what the answers are. No, no, so it's neither one of those. Yes. Yes, because the relative frequency of the higher tar classes is greater for non-filtered cigarettes. This cannot be determined is, of course, wrong. So that was only yes. That's the only one it could be.